thank you so much, Suman, and thank you so much, Panigrahi sir. So I am going to talk about this high fidelity generation of Fock state in a cavity. And I am Dr. Nilakantha Meher from SRM University, Andhra Pradesh. I may not take an hour, but let's see how much it goes. So I start from a very basic level from the scratch. That is our classical harmonic oscillator that is well known. As you know, this suppose a mass is attached to a spring with a spring constant K. We know that this mass oscillates in time. And this is the position evolves, how it evolves, that is sinusoidally. This is the omega is the resonance, this frequency, you can say, frequency of the oscillator. And due to this restoring force, this oscillates forth and back and forth. And this phi is the your initial phase. Here you can see this energy is continuous here. That means it can take any amount of energy. And frequency is also, any frequency is allowed. There is no restriction at all. And the ground state energy is 0 if you think the oscillator is classically. Okay. Now let us go to quantum harmonic oscillator. Let us describe this oscillator in a small scale in quantum mechanics, and let us see how it changes. If you go to quantum level, this is the Hamiltonian for the harmonic oscillator. And what we have done actually here, this position and momentum are replaced by operators. There it was a classical variables, and it is now replaced by operators P cap and X cap. Okay. So to quantize this harmonic oscillator, we define two operators. One is annihilation operator, another one is creation operator. By combining this X and P, here it should be X actually. I wrote Q, but it should be X here. By combining this position and momentum operators, we can define two operators, that is, they are annihilation and creation operators. And now I can write this Hamiltonian, total Hamiltonian of the harmonic oscillator in terms of given here, where A dagger A is the number operator. And let us denote this eigenstate of this number operator, that is cat n. Okay. This cat n also becomes the eigenstate of the Hamiltonian. So therefore, it clearly says that the energy levels are now equispaced and quantized. It is no longer continuous. It becomes discrete. And this cat n is called Fock state or number state. So you can see here, energy becomes quantized, that is discrete, and any frequency, still any frequency is allowed. There is no restriction on frequency for the quantum oscillator. And what the changes here is that ground state energy is now no longer 0. It is half h cross omega, where omega is the resonance frequency of the oscillator. And what is the importance of this oscillator? We know that any arbitrary potential to a local minima, near to local minima, this point x naught, we can approximate to a harmonic oscillator potential, that is parabolic form. Okay. And its dynamics can be understood in terms of harmonic oscillator dynamics. And there are systems which are equivalent to harmonic oscillator. And one such system I'm going to talk here, that is electromagnetic field. And I will show you how this electromagnetic field is equivalent to a harmonic oscillator. And these are well-known Maxwell's equation. There are 4 Maxwell's equations. The first one is Gauss law, that says about the node here, at least in this is in free space. That's why it is absence of charge and current. So del dot E equal to 0. It's supposed to be rho by epsilon naught here, but as there is no charge and no current, so you can write del dot E equal to 0. That is no divergence. Similarly, del dot B 0 always in the absence of charge or in the absence of current also. So you can say that from this equation signifies that no monopole exists. So that means you cannot get separately North Pole and South Pole. And del cross E equal to minus del B dou B by dou T. This says that change in magnetic field creates electric field. Similarly, the last equation says that change in electric field also generates a magnetic field. And these are the corrected by Maxwell's equation. Here one term should be there, that mu naught J, but as I'm talking about absence of current, that current density becomes 0. So that's why del cross B equal to only this term. And this is corrected by Maxwell's. So this electric field and magnetic field satisfy a wave equation. Separately, they satisfy a wave equation. That means we know that essentially this 4 Maxwell's equation gives the idea about this electromagnetic wave. Now consider a cavity. Okay, cavity means 2 mirrors, and this electromagnetic field is traveling along z direction. This is the z direction. It is traveling along z direction, and these 2 bars suppose they are the mirrors, which is placed at z equal to 0 and z equal to L. It is confined to one-dimensional cavity of length L. So what is a cavity essentially? Cavity means two highly reflective mirrors. They are facing each other. As you can see one figure here I put here. So these two mirrors are facing, mirror 1 and mirror 2. This you can call the cavity because it can trap the photons or trap the electromagnetic field for a long time. Now this, as we are confining this electromagnetic field inside a cavity, the solution of this electromagnetic field, that is electric field and magnetic field, as given here. Okay, so the spatial part varies as sinusoidally, whereas of course there are temporal part also. Let us take Q of t and Q dot of t, and they satisfy the Maxwell's 4 equations. Now apply the boundary condition, that is electric field mostly tangential component must vanish at the mirror surface, as they are highly conducting surfaces. The mirrors are highly conducting surfaces, so this electric field should vanish at the mirror surface. If you put this condition, this restricts actually number of frequencies allowed inside the cavity. So this restricts the frequency. Not any arbitrary frequency can stay in the cavity. So that means it says that any arbitrary field cannot sustain inside the cavity. The frequency of the field must satisfy the above condition. And I have given some that the frequency will satisfy this condition. But of course, one can have several frequencies. But you can see here, electric field vanishes at the boundary. You can see here. Okay. Now let us calculate the energy of the electromagnetic field. Single mode field means it has single frequency, of course single wavelength has to be there. Single frequency means single polarization and single propagation direction. That you can call that one as single mode field. Now if you calculate the energy of the electromagnetic field, okay, using this solution, whatever I showed this one, using this solution, this Ex of t and By of t, mostly you can take Ex of t. It shows that the electromagnetic field this energy of the electromagnetic field can be written as harmonic oscillator Hamiltonian, classical harmonic oscillator Hamiltonian, where I replace P equal to Q dot, that is scaled with mass. It's just a quantity. Then you can say that electromagnetic field inside a cavity is equivalent to a harmonic oscillator. Now, similarly, the same quantization procedure follows here, because already we know how to quantize the harmonic oscillator, classical harmonic oscillator. Similarly, we can quantize the harmonic oscillator for electromagnetic field also, because as I already showed that this electromagnetic field is equivalent to a classical harmonic oscillator. Now you can define two operators, but here we have given the name as photon annihilation operator A, and A dagger is a photon creation operator. Similarly, I can write the Hamiltonian quantized version of the Hamiltonian for the electromagnetic field, and here A dagger A is the photon number operator. Here something changes here. You can see here the energy becomes discrete as like harmonic oscillator. It's no longer continuous, it is discrete, and it satisfies n plus half h cross omega. But you can see here frequency also becomes discrete. No arbitrary frequency is allowed inside the cavity. It depends on the length of the cavity. And ground state energy is, that is again non-zero, and this is called vacuum field energy. So in the absence of photon, this is the energy you get for a single mode field, half h bar omega. Now let us denote n again, once again, the eigenstate of the photon number operator and the Hamiltonian. And this n we will call as photon number state or Fock state. Okay. And let us try to see how we can generate this optical photon Fock state. This cat n represents the field containing n photons, exactly precisely n photons. Okay. And this A and A dagger, what are the actions of this one? This will subtract a photon, one photon from the cavity field, and A dagger will add one photon to the cavity field. This is the action of A and A dagger. Now I will discuss about the preparation, how we will prepare these Fock states or number sets by various methods. First, let us try to see, can we drive a cavity by a laser, and let us see, can we generate a Fock state. Second, I will discuss, can we generate photons, so Fock state using atoms, and there is something called photon blockade mechanism. Can we generate Fock state using that photon blockade mechanism? And finally, I will discuss our scheme, that is, how to generate Fock state using Kerr and displacement operation. So let us see, can we generate a photon using driving the cavity? First, consider the cavity in a vacuum, that is no photons are there, exactly, that is no photons are there. And now drive the cavity by a laser with frequency omega L. And this is the Hamiltonian for the corresponding system, that is a cavity, single cavity, that is harmonic oscillator Hamiltonian plus the driving term. A plus A dagger is a driving term actually with the frequency omega L. Under resonance condition, that is omega L and omega L equal to omega. That means if the cavity resonance frequency matches with the cavity this laser frequency, then under this resonance condition, I can write this Hamiltonian in rotating frame. That is only H cross epsilon A plus A dagger. This is the simplest version of this total Hamiltonian under resonance condition. Now let us see how the cavity evolves in time. So of course, this epsilon is a driving strength here. So as the cavity started in a vacuum state, that is cat 0, now it is evolving with unitarily. And this gives a state alpha. I'll tell you what is the alpha. Essentially, this alpha is the coherent state. And how it looks in photon number basis, this is a superposition of all the number sets. This coherent state is a superposition of all the number sets. We can see here the photon number distribution is a Poissonian photon number distribution. So that means there is this coherent state contains not a precise photon number, it has a distribution of all the photon number sets. Of course, it depends on the amplitude of this coherent state, this alpha, where alpha is the I epsilon t, and of course epsilon is the driving strength. So essentially says that how strongly you are driving, accordingly you will create a coherent state with the photon number distribution given here, which is Poissonian photon number distribution. And of course, and all possible Fock states are present here. So that means this driving is not able to generate a particular Fock state. It is generating all possible, so essentially superposition of all the Fock states, all the number states. Okay. Why it is happening? Because this is a classical, this is not a classical, this is harmonic oscillator. This cavity field considered as harmonic oscillator. It has equispaced energy levels. Okay. So if you start from a 0, when you're driving, it can jump to 1 and 2 and 3 because of it is resonance in all the frequencies. This energy space are equispaced, so it essentially drives from 0 to any photon number. So that means that's why we are getting the superposition of all the photon number states because of this signature. Now let us try to prepare this for. So essentially, I can conclude here that cannot create a particular Fock states or number state. So let us see now, can we prepare these number states or Fock states using atoms? Once again, assume the cavity is in empty, that is in vacuum state, and send an atom through the cavity, okay, which is in excited state. Now, if you send this atom, essentially what it does, while traveling through the cavity, it can give, as it is an excited state, it can give one photon to the cavity, and it will come back out of the cavity. So now, if you detect this atom in the ground state, then you are sure that the cavity has single photon state. So essentially, we are able to prepare a single photon Fock states by sending an atom through the cavity. Now let us see mathematically what is happening. So our initial state is E cat 0. E means that is the atom in excited state, and 0 is the cavity in vacuum, that is no photons. This is, I'm not going to details of this Jans-Cummings interaction. So simply I just say that. So this is essentially, this model essentially explains how an atom interacts with the cavity field. So you can see the first term, this explains this emission of photon from the atom to the cavity, and second term explains the absorption of the photon from the cavity. So essentially there are two terms. This is an interaction term which explains the emission and absorption of the photon from the atom to the cavity, and where G is the atom field coupling strength. This G is the atom field coupling strength. Now, because of this interaction, that is Jans-Cummings interaction, our initial states evolves as follows. So it will be cosine GT. That, of course, that's cos square GT will be the probability of finding E0, and sine square GT will be the probability of finding G1. You can see here G1 state is coming because the atom can emit the photon to the cavity and atom goes to the ground state. So that's why there are two possible cases, E0 and G1. And there is, as we are not driving anything, so these are the two possible states only. E0 can go to G1 with the probability of sine square GT. Now, select this velocity. So this atom is going through the cavity, right? So what you'll do generally, select this velocity in such a way that it exactly spends pi by 2g time. Okay, this much time it spends. G is the atom field coupling strength. So exactly it spends pi by 2g time inside the cavity. So that what happens when you put this time t equal to pi by 2g, this term survives, G1. So my state now evolved state is becomes G1, and in this time this atom will come out, And if you detect this atom in ground state G, then we are sure that the field contains exactly one photon. So you can able to prepare a single photon state. Now to prepare higher order Fock states, now we can send another atom. So now initially the cavity was one photon already prepared, one photon. Now once again send the atom being in excited state E. Similarly, it follows that the initial state as E1 because atom in excited state, and already we have prepared one photon Fock state. So now this state evolves as this one. Now it is connecting, you can see here G2, that is atom can go to ground state and it gives one photon to the cavity. So that becomes two photons. So similarly here we can precisely set the time, that is pi by 2 root 2g inside the cavity in such a way, then the state evolves to E1 to G2 at exactly this time. So in this case, again, if you detect the ground state, detect the atom in ground state, then we are sure that cavity state becomes 2, that is 2 photon state. So in this way, by sending so many atoms, we can prepare n photon Fock state similarly in this same procedure. So what are the limitations here actually? One limitation is that the atom may not emit the photon to the cavity, it may emit to the environment. In that case, we cannot prepare, we'll be thinking that we are preparing n photon, but it may be some n minus or n minus 2 photons because we already lost the photon to environment. Another way is that the atom may emit and reabsorb a photon again. So we may not detect the atom in the ground state. And also you need to control the time of interaction precisely, that the atom is traveling through the cavity, right? So you need to control this time precisely. Then only you can prepare these Fock states. Now let us go to, of course, if these are the limitations, then preparing a large Fock state is really challenging. And now let us go to how we can prepare these Fock states via something called photon blockade. For this, we need a cavity containing a Kerr nonlinear medium. Okay, Kerr medium is that is intensity dependent medium. So the cavity is driven by a laser also. First thing is cavity contains the Kerr nonlinear medium, and the cavity is driven by a laser frequency of omega L. So this is the Hamiltonian. The first term is nothing but your harmonic oscillator Hamiltonian linear term, and the second term is your Kerr nonlinear term, that is a dagger whole square, essentially intensity dependent kind of things, a dagger whole square, and this chi is the Kerr strength. And of course, this is the driving term that already I discussed, that is epsilon a plus a dagger. Now let us look the energy levels, whether these are really harmonic, that is equispaced energy levels, or what is happening. If you calculate n photons energy of n photons in this case, in this system, in the presence of Kerr nonlinearity, it is linear term is there, that is harmonic oscillator energy levels is there. Also there is energy term that is KLSS n square. So it is not n linear, it is non-linear and it is going over n square. So it is no longer a harmonic level system, that is equispaced energy, rather it is an harmonic system. You can see their energy levels are not equispaced. Of course, I have not drawn for level 3, level 4, all these things, but I have showed only up to level 2. You can see, still you can see here, the energy levels are no longer linear, that is equispaced because of this Kerr strength. But once you fix this Kerr strength 0, then automatically I will get that energy levels are equispaced, that is harmonic energy levels. And because of this non-linearity, it becomes anharmonic, that is energy levels are not equispaced. In this case, if you drive a laser frequency which is resonant to only 0 and 1, suppose, okay, that is I have to fix this omega L resonance frequency of this omega plus chi term, that is you subtract this U1 minus E0, the energy. So this will give you the how much frequency I have to drive such that it will give the transition from 0 to 1 only. And because of this far off resonant from 1 to 2 or 0 to make a transition to level 2 or higher levels. So that means I can drive the photon only from 0 to 1. So essentially what is happening inside the cavity? You have a Kerr nonlinear medium and you are driving by a laser with a frequency omega plus chi. So what is happening actually? The presence of one photon inside the cavity essentially blocks the other photon to come into the cavity. It means cavity can have only one photon at a time. It cannot have two photons or more than one photons. So this is called essentially photon blockade. This photon, that single photon present in the cavity, is blocking other photon to come into the cavity. So that's why we'll call as photon blockade. Now, if you want to prepare higher order Fock states, now you're driving a resonance frequency, the cavity by resonance frequency, which is matches with the the spacing between 0 to 2, that is energy difference between 0 to 2. In that case, only transition can occur from 0 to 2 and transitions to any other levels. In that case, we can prepare a 2-photon Fock state. That is precisely 2 photon I can prepare by driving the cavity with a frequency of 2 omega plus 4 chi. Similarly, if you want to prepare n-photon Fock state, then we have to drive the cavity by a frequency of n omega plus n square chi, so that it can connect the 0 to n photon level, and you can prepare n-photon Fock state. So what are the limitations here? Essentially, to get an enharmonic system energy levels, we need a large Kerr nonlinearity strength. Okay, that's why generating large Fock states is difficult. Of course, small Fock states you can easily prepare, but large Fock states it is difficult. Now coming to our scheme, that is how to use this Kerr interaction, that is Kerr nonlinearity and displacement, we can prepare the Fock states. So let us check first mathematical formulation. Let us consider a coherent state, and we know that coherence is the superposition of all the number states. There is no definite photon number. It has a distribution, that is Poissonian photon distribution. Okay, now we apply Kerr unitary operator, that is a dagger square a square. This is the Kerr unitary operator. Of course, I will discuss the experimental feasibility, but let us do the mathematical formulation first. Okay, so you apply this Kerr unitary operator on the coherent state, and this is the calculation. Okay, so this is all same superposition, all these things. This unitary operator essentially a dagger square a square is the essentially this ket n is the eigenstate of a dagger square a square. That's why it is pulling out this exponential term, that is e power minus I chi n into n minus 1 t. Okay, if you see this state, although state changes, but it does not change the photon number distribution. The same photon number distribution is obeys, that is Poissonian photon number distribution as like coherent state. Of course, it has changed the state, but the photon number distribution is same. So that means only Kerr unitary cannot prepare a Fock state, because again you have got the Poissonian photon number distribution. Then there is no precise Fock state or photon number state. Now let us consider another operator, that is displacement operator. What it does actually, this is the displacement operator. In quantum optics generally we write in terms of a and a dagger. What it does actually, if you apply on a coherent state alpha, it displaces the state to alpha plus beta. Whatever the amplitude you are displacing, it essentially displaces the coherent state. What does it mean? You have a photon number distribution, initial photon number distribution. Once you displace, the photon number distribution will displace to the some other amount, depending on beta, how much you're displacing. That means essentially you are adding some more energy to the system, displacing the photon number. So again, it is a coherent state. This coherent state remains coherent state because of displacement operator, and the new amplitude becomes alpha plus beta. So your intensity becomes essentially mod of alpha plus beta mod square. Okay, so this is the new intensity, but the state remains coherent. There is no changes. Now, what we do actually generally, what it does, that we combinedly operate them on a coherent state. That is Kerr interaction and displacement operator. Suppose we combinedly interact. Initially, we saw that in the before 2 slides, we saw that individually they are not able to change the state. Their photon number distribution remains Poissonian. Now let us see if we combinedly operate them. That means first apply Kerr unitary and then displacement operator. If we apply this one, that is Kerr unitary is applied first, then displacement applied second. This is the resultant state. If I see here, this combined operation changes the photon number distribution. Okay, and the state is no longer a coherent. It is no longer a Poissonian distribution, no longer a coherent, and it changes the photon number distribution. I will show in the next slide that if you see this one, so alpha goes through a process like Kerr unitary and then displacement, and it gives a state psi of 1. So here, why I have written 1, we are combinedly we are telling that this is a 1 iteration. Okay, subsequently we'll give some more iteration. So I'm telling that this combinedly operating this Kerr unitary and displacement, I am telling this one as 1 iteration. Okay, and one iteration itself changes the state from Poissonian to a non-Poissonian distribution, some other distribution. Of course it changes the state, but still we are not able to get the Fock state. You can see. Okay, so as we are interested in n-photon Fock state generation, let us calculate what is the probability of finding n-photon state in the resultant state. That is acting of this U chi, that is Kerr unitary and displacement operation on coherent state, and try to calculate what is the probability of finding n-photon state on that resultant state. And this is the photon number. This is the probability given here. For a simple case, let us try to prepare a single photon Fock state. Can we prepare single photon Fock state? And let us see how much probability we can go in a single iteration. So we optimized, essentially, we chose alpha equal to √1, beta and chi is optimized over here. And we saw that we can reach the probability of finding a single photon up to 0.8. That is the maximum we can achieve in this single iteration.
What is the difference between capital N and small n?
This small, okay, this small n you are saying?
Yes, small n and capital N.
Yeah, capital N is the particular Fock state where we want to generate. And small n is the varying 0 to infinity. So all the photons number. Am I clear?
So you are generating now a single photon, huh?
No, not yet. Okay, for simple case, I'm telling the single photon, that is n equal to 1. Okay. So we put n equal to 1 here and let us try to calculate what is the probability. Okay.
Yeah.
So that is what essentially. So as an example, I've taken here. Let us try to prepare a Fock state 1. And we saw that for this beta and chi, this is giving maximum achievable probability, that is 0.8. Okay. Now to prepare, suppose n photon, that is 2 photon Fock state. That is, I fix capital N equal to 2. And I saw that whenever I'm setting alpha equal to √2 and beta and chi pi this much, I could reach only 0.73. This is the maximum I can reach the probability. So what our observation is that it is not possible to generate Fock states with unit probability in a single iteration. That means apply this K-unitary and displacement approach only once. That is a single iteration for us. Okay. And to generate, what another observation we saw, that to generate n photon Fock state, we must choose alpha equal to √n. As here you can see here, whenever I'm choosing alpha equal to √2, then only I'm getting a maximum value. Similarly here also, in the first case also, whenever I'm choosing alpha equal to √1, that is alpha is nothing but for my initial coherence state. Keep in mind, okay? Alpha is the amplitude of initial coherence state. That is my cavity starting point. So whenever I'm choosing this alpha equal to √n, then only I'm getting some maximum probability. Although it is not near to unity, but some getting maximum probability. So therefore, we fix from now onwards alpha equal to √n for generating n photon Fock state. So this is one, that is one variable is fixed now, that alpha equal to √n to generate n photon Fock state. Now consider another iteration, that is, once I applied this one d beta 1 u chi 1, that is the K-unitary and displacement. Once again I put another iteration. And I got the, suppose the state is psi 2. I represent the state, the resultant state is psi 2. Now let us calculate the probability of finding n here. Although this looks very cumbersome and you could not further simplify actually, and one can take challenging this one because it is really challenging to further simplify. I could not get a simple expression as given here. So that means here we need to optimize over 4 variables. That is beta 1, beta 2, that is driving amplitudes, and K strengths, chi 1, chi 2. To maximize the probability for a given n. And we numerically optimize, and this is the table source. We can see here for 2 iterations, we could reach the probability up to 0.97 for single photon state, and remain, of course, it decrement from the 0.97 to 0.91. And of course, when you go further higher order Fock state, up to 6 photon state, we could achieve the probability of finding Fock state more than 0.9. In the second, that is 2 iterations. And we cannot, if you want to generate higher order Fock states, then this probability may decrease because only 2 iterations. So now let us try to further increase one more iteration, that is 3rd iteration, d beta 3 and chi 3. So this is the probability again to calculate. Of course, again, once again, I'm saying sorry that we cannot simplify further because there are so many summations are there. And again, here we need to optimize our 6 variables, that is beta 1, beta 2, beta 3, driving amplitudes, that is driving a beta 1, beta 2, beta 3, and K strengths, chi 1, chi 2, chi 3. Surprisingly, this enhances, we can generate up to 20 photon Fock states with the probability more than 0.95. So this essentially improves the fidelity, as well as we can generate higher order Fock states up to 20. So okay, so you can generate up to 20 photon Fock states with a 3 iteration, and the probability fidelity becomes more than 95. I'll show you how this probability distribution evolves for a given example. That is, suppose I want to generate a Fock state 3. So I choose alpha equal to √n, that is √3. And you can see here this alpha goes three iterations, that is m1, m equal to 1, that is u chi k1, carotary displacement, again another iteration, again another iteration, third iteration. And you can see this probability distribution here. This is the initial distribution, okay? That is the coherent state Weizmann distribution with alpha equal to √3. Once I apply that is care and displacement, after first iteration, this is the probability distribution. It looks like this. The second iteration, slowly, gradually narrowing down towards 3. And the final iteration, that is after third iteration, the probability reaches up to 0.97. You can see other photon numbers are negligible. So you can say that we can very closely generate Fock states with this 3 iteration. And I can say, if you want to increase the number of iteration, then we expect that the probability may be improved, and you can generate also more than 20 photons. So now let us go to the experimental feasibility. So what is the situation here? Let us take a cavity which consists of Kerr nonlinear medium, and the Hamiltonian is given here. That is a dagger square, a square Hamiltonian, and this kappa, capital kappa, is the Kerr strength. Now, so the unitary evolution for this one is that given here. This is we are calling as Kerr unitary operator. So the evolution in the Kerr nonlinear, the free evolution in the Kerr nonlinear medium is, you can call this one as Kerr unitary operator. Now, this cavity is driven by a pulse laser, okay? That is ultra short pulse laser pulses, and you can show that this ultra short pulse lasers are equivalent to displacement operator here. And this proof is given in our paper. Actually, I'm not going to discuss that one. So what we got here? We got a cavity with Kerr nonlinear medium, and we are driving this cavity by 3 laser pulses, that is by a pulse laser at different time. And also we have proved that this laser pulses, that is ultra short laser pulses, are equivalent to displacement of the cavity. So now we can see the unitary evolution up to the first pulse, that is T1, up to the first pulse. We can write that the Kerr evolution, the free evolution, Kerr evolution, and the amplitude with a beta1, driving amplitude up to the first pulse. Now, if I see the unitary evolution up to the time, that is T2 minus T1, in between this one, that is again free evolution with the Kerr, again the driving amplitude will be d beta2. The second pulse is gone. So this is the first pulse d beta1, again freely evolved, that is Kerr unitary evolution. The second pulse has gone at time T2. Now in the third unitary evolution, that is again the cavity evolves for some time, that is T3 minus T2. Again we have given a pulse at T3, exactly T3, that is with the amplitude d beta3. And this 3 unitary evolution exactly equivalent to our what I discussed earlier, that is 3 iterations, Kerr unitary evolution and displacement evolution or displacement operation. Okay. Now if you look it properly, these unitary operators, you can see here this kappa T1 is equivalent to our chi1. That is, I was using chi1 terms in that earlier discussion, the mathematical formulation. So this so whatever the chi, I have given these variables, right? So these parameters are given here. This chi1, beta1, beta2, chi1, chi2, all these things. So if you match these experimental values, that is K, this capital kappa time T1, that is time of, that is where the pulse were driven to the cavity. If this KT1, that is kappa T1 is equal to chi1, then you can say that this exactly this first iteration is equivalent to our the display, that is pulse, laser pulse at time T1 with the free evolution, that is Kerr evolution. Similarly, if the K times, that is kappa times T2 minus T1 is equal to chi2, if you can match this one, then this, of course, this evolution, that iteration is second iteration is equivalent to our that pulse as well as free evolution of Kerr term. Similarly for this third iteration. So it is equivalent to iteratively applying a displacement operator and a Kerr unitary operator. This essentially these evolutions. And by properly choosing this driving amplitude, that is beta1, beta2, beta3, and pulse interval, essentially here kappa I fixed kappa, and I have varied T1 and T2 minus T1 and T3 minus T2. If I properly choose this timing of pulses, then you can say that this will be equivalent to chi1, chi2, chi3, and we can say that this 3 evolution becomes equivalent to 3 iterations, which will be acted on alpha, that is coherent state, initial coherent state, which will give you a particular Fock states alpha. If alpha equal to root n, then you can get a Fock state of that particular Fock state with high probability. So now I'll summarize this one, that electromagnetic field inside a cavity is equivalent to a harmonic oscillator, and Fock states, that is number states, are the eigenstate of harmonic oscillator Hamiltonian, and generation of large Fock states are really challenging by driving. That driving cannot generate Fock states, but atoms and photon blockade mechanism can be used to generate smaller Fock states, and our scheme, that is Kerr unitary and displacement operation, combinedly can generate large Fock states with high probability. So I'll stop here, and thank you so much for listening. And if any questions, then
thank you, Professor Meher, for this nice pedagogical lecture. And so the time for the questions. So participate. You can unmute yourself and ask the question.
Yeah.
I have one comment.
Yeah, sure.
So, yeah, thank you for a very interesting and informative talk.
Yeah,
so,
welcome, sir.
Thank you. Such type of calculations have been considered.
Okay.
I mean, in the paper in 2025.
Okay.
And where chip-based Kerr waveguides are proposed. So in your case, you are proposing cavity. So this was done, and so in that paper, instead of 3 displacement, you can use 1 displacement by by optimizing Fano factor or Mendel parameter.
Okay.
So you can reduce 3 iterations to 1.
Oh, so that is okay. I will see which one you are referring. Which paper referring actually? Any idea? Anything?
Yes. Josabi.
Josabi.
Volume 42.
Okay, 42.
Issue 11.
Okay, 11.
And page B10. Or
okay, B10.
you can also use the similar version is present at archive also. 2501.
Okay, so okay, fine.
.02405.
Okay, fine, perfectly fine. Thank you so much. I will definitely look over this, and if any further, if you can reduce this number of iterations, that is the best actually. Yeah, that is the best. So
yes. Thank you.
Welcome.
Thank you, Singh, for your nice comment. So we have few questions from our participant. Manjit, you can unmute and ask question. Otherwise, I can read your question.
Okay, so what is rotational mechanism? Slide 13. Okay, slide number 13. Okay, so this is essentially, I am saying that in rotating frame, that is essentially, so in the laser frame, we are going to see it actually, how it looks. Maybe experimentally, I don't know what is that experimentally. Generally, they say rotating frame. So this is the, from my perspective, I would say this is the mathematical simplification. But in a rotating frame, in a sense, like, you know, this energy levels, whatever the energy, these terms are there, this free evolution term. So those terms essentially, it is become like, you know, when it is become resonance condition, this delta, it will come, one delta will come here, okay? And that delta equal to 0 because this is resonance. Delta is nothing but your omega L minus omega. So when resonance condition, this first term will go, and only the one single term will be there. Of course, I don't know really this experimentally what is the meaning of that this rotating frame. So this is really a difficult question actually for me also.
So
next question. Interference between different photons. So because you find 6 photons, you are able to generate in the cavity with a good probability distribution.
Yeah.
But what about the photon-photon interaction within the cavity? How do you prevent that?
This due to Kerr nonlinearity?
Yes.
Yeah, due to Kerr medium, yes, there are photon-photon interaction will be there definitely. Because of this only actually because of this interference only we are able to generate these 6 photons. There are. That's why these energy levels are not equispaced also.
Okay. So question is when you take the probability distribution, you have the factor of variance for alpha by 2.
Probability distribution, yes, minus alpha by, minus mod alpha square by 2, yes.
So why should we take it within the modulus? Can't we take it outside the modulus?
You can take it out. That is I wrote that way, but you can take it. It will be minus e power minus mod alpha square. That's all. You can take it out. Yes, there is no problem. Yes.
Okay.
You can take it out.
Okay, fine. So I had to answer about it. Thank you. Thank you.
Welcome. And another question was there actually.
Yeah,
do you work on non-Gaussian quantum optics for application in CV-based quantum computing? Okay, non-Gaussian quantum optics. No, CV-based quantum computing I'm not working actually, but this is a very nice area. This is recently people are working on it. I'm not working here. This continuous variable based quantum computation.